But what you see in the museums are the suits that they practice with.
Yeah.
Because the actual suit, an Apollo suit, with the PLSS would be around 100 kilos, something like that.
Yeah, that's pretty close, yeah.
It's actually 180 pounds. The suit was about 45 pounds and the PLSS was 140.
Yeah.
Well, when they're on that in a full simulation and you see them with the suit on, when they're on Earth practicing, there wouldn't be anything in the PLSS because you don't need it.
Yeah, exactly.
Because you're on Earth practicing.
And it'd be too heavy.
A fan to blow some air around inside.
Yeah.
A little bit of a battery in your communication, right? Keep you cool, like practicing on Earth. And the rest of the suit would be a lot lighter. You wouldn't need 45 pounds of suit on there for practice. But when you look at the suits in the museum, that's all you see.
Mm-hmm.
Like the zippers don't even go up tight. Like there's about an inch and a half short at the back where it zips up to the back side of the helmet. That wouldn't seal.
That's the other thing too, and this is just purely common sense here. When you talked about this before, and I've always found it fascinating when you talk about the zippers in the suits, that how did they make sure, and it'd be too long to go into this right now, but I want people to think about this, or I'm asking people to think about this. How did they make sure that there wasn't any seepage from the atmosphere of the suit to outside, keeping in mind the hard vacuum of that environment on a lunar surface? I mean, these are all questions that NASA doesn't answer.
Who's that Paulo Altavistimo? He's got a whole thing in his thing on the zippers and stuff, right? He's taking scuba diving zippers.
Yeah.
And of course, some of the Apollo suits that they practice with were in water tanks.
Yes.
So they would have had those on there.
That's right.
That's where they came from. The suits in the museum do not have any rubber on them.
And that's NASA's reply, by the way, to people who question, did you test the suits in a vacuum chamber? They said, well, we tested them underwater. And they tried to make that as adequate in lieu of testing the suits in the vacuum chamber. They tested them underwater, but they're two different environments here. They don't even compare.
What people need to understand is the difference between having a pressurized suit in a vacuum and being underwater. You don't need any structure in the suit to be underwater.
No.
Because you are using pressure inside the suit and match the pressure of the water. And when they're equal, there's no pressure on the suit itself. When you're in space, you have pressure inside and the vacuum on the outside, or complete lack of, right? And then you have now combined force.
See, that's a very good point. And also to keep in mind for people that when the astronauts are testing those suits underwater, it's equivalent to, let's say, an Olympic-sized pool. We're not talking a lot of pressure per square inch on the suit as opposed to if you were testing them deep in the ocean to come to some kind of, and again, there's no real comparison between what the atmospheric pressure is in the ocean compared to what you would have. You would have the opposite in the vacuum of space, but there's really no good comparison that NASA has been able to come up with other than to admit that they did not test these Apollo suits in their vacuum chambers.
Well, even today, no one has been inside the Glenn Research Center when that thing's been turned on. If vacuum is such little force, they should just have an airlock. People get in their suits, they go through the airlock, go inside, do all their practice, get 30, 40, 50 people in there working all the time, because it's 150 feet across this chamber.
Yeah.
Right? So you can put a lot of people in there and put equipment in and everything else and run it all through an airlock.
Yeah.
Right? People can go in and out, and they'd be testing the suits, they'd be able to practice on the stuff, they could test all kinds of equipments, experiments, everything else in there. Nobody does that, because they can't put an airlock on that. And that's only at 130 miles up, that force. Now you have to think how strong the vacuum is when you go out farther, because you have to match the strength of the structure of that building. The Glenn Research Center is only holding back one atmosphere on the outside.
Yeah.
That's all it is. Now, when you're looking at the structure, something should be clarified, right? To be as strong as that is based on the surface area that you're dealing with. The average thickness of the walls in the Glenn Research Center is about 10 feet. The diameter is 150 feet. You have a ratio of 15 to 1.
Didn't they put the command service module in there to test it, if I'm not mistaken?
Well, you have no idea how far they pulled it down or whether they even had the thing pressurized inside. If you leave the door open, you can put it in a vacuum chamber and nothing happens, right?
Yeah, exactly. That's why I didn't talk a lot about that in my books, is that I haven't actually looked into that aspect of it because there was so much other things that I had covered that would have told me it would have failed anyway. But how much testing did they do, just as a side note here, how much testing do you know, that, if any, that they do on a command service module in the vacuum chamber?
I don't know what they were testing when they put it in. I haven't seen a whole lot of documentation on it, and there's certainly no detail.
Yeah, exactly.
Okay? Because they could put it in, leave the door open, and say, well, we're pressurizing the fuel tanks.
For sure. That's why I left that out, because I didn't see a lot of detail in it myself. And you're right, and they can say anything. Given what else we have discovered along the way, I mean, they could just, you're right, they could say anything in terms of that.
Back to the vacuum and the dimensions and the surface area involved.
Yeah.
Right? If you take the Glenn Research Center, it's 15 to 1.
Mm-hmm.
150 feet across, 10 feet of wall.
Yeah.
So if you bring that down and you say, okay, the ISS is 15 feet across, so it should need a 1 foot, or the strength of 1 foot, like whether the skin and the ribbing and everything else equals that, right?
Right.
You take a look at Mythbusters, right? They pick a vehicle up using a vacuum cleaner, shop vac.
Mythbusters, they've been discredited a few times now.
But what they did by mistake, what they actually showed you, is they just had little quarter-inch plastic lines.
Right.
Those quarter-inch plastic lines are picking a vehicle up without collapsing.
Interesting.
Because the surface area is so small compared to it, and the wall thickness of the plastic to the dimension of the hose that they're using. But they're not using one of them, they're using 500 of them or whatever they took to pick the thing up with, right? So it's a combination of that. The vacuum cleaner, the tank did not collapse, yet it picked it up. It's based on the total surface area that they put on the vehicle that allowed it to pick it up.
And you see, this is the point for people watching, this is the point that Scott is making, is that there are so many fine details that even some you can do yourself in terms of experiments, which Scott, Robert, and Marcus have done. And including another researcher, Jared White has done that too. He's done some work, has tried to, and successfully, I think, has discredited Mythbusters in their attempt to discredit what they call conspiracy theorists when it comes to the Apollo missions, but actually backfired on them. So this is the point. There are a volume of details when it comes to this subject that it would take you years, but all you have to do, don't overwhelm yourself, all you have to do is just look at a few of the details. As Scott mentioned, the photographic record, the film record. But I just want everybody to know that this can be an overwhelming subject when it comes to the Apollo moon missions, and it's a rabbit hole to go down for sure. But you don't have to look into everything. Just pick some of the details that you like and look into that and go from there. You don't have to cover everything. Don't listen to the proponents. Always like to come back and say, well, what about this, and this? And your answer would be, well, I'll get to that in due time, but what about this? You see, their way of avoiding some of the anomalies that Scott has brought up would be to say, well, okay, well, what about this? And so they try to cover. They don't have a response to Scott's work, so they come up with what about this? But they did this and this and this, and that's how they do it. Is they try to distract and divert you away from that. Before we wrap up, I want to get to the Saturn V, which I found interesting. I'll let you take it from here.
Well, you've got the expert knowledge on the Saturn V, and I have looked at it, and what I wanted to talk to you about is what I came across when I was reading some of the detail, because I was looking at the different orbits that they were taking, and I had discussed that before when they said they went around the Van Allen belts and that, so I was looking at some of the new documents to see if they've changed it again, and of course all their drawings go right straight through the center of the Van Allen belt, right? They didn't move around it.
Yep.
So when they're starting off, once they get into low Earth orbit, they've already fired the third stage once. Now, the tanks on the third stage are fairly small because it's housing the payload. It has the LEM and the CSM command module. It's all inside of that. So it has very small fuel tanks, and it's already done one burn to bring it from, 105 miles or something to 125 miles. And then it does the next burn where it accelerates the vehicle into translunar insertion.
Yeah.
Right? But it does not reach enough speed. It only gets to 25,000 miles an hour when it runs out of fuel.
They actually shorted that, I think, wouldn't it? By 24 and a bit.
Yeah, it's 24 something,
yeah.
Right?
Yeah.
And they need 27 to get escape velocity so that they can coast, so they don't need any more power the rest of the way.
They go into an elliptical orbit, though. Is it 27 or is it 24?
They're done the elliptical orbit when they do the burn.
Right.
Now they're going to head straight out.
Would that not technically be an elliptic orbit when they include the orbit around the moon? I think it's an extension of Earth's orbit.
When they do so-called an elliptical orbit to gain speed around the Earth, then they do the burn. It gets up to less than nominal speed with the third stage because it's out of fuel, because it has small fuel tanks.
Yeah.
So they vent those tanks out so they wouldn't have an explosion, that there's no fuel left. Out comes the CSM, it turns around, goes in, grabs a hold of the LEM, pulls it out, then it turns around again, and the CSM does a burn to bring it up an additional 2,000 miles an hour so that it has escape velocity on this translunar injection. And then, of course, as it coasts through, it gets down, and by the time it gets to the L zone, and that's where the gravitation of the Earth and the Moon are equal, it's down to about 2,000 miles an hour.
Yeah, 3,000, that's right.
And then it speeds back up to about 6,000 miles an hour, and that's the speed it goes into orbit around the moon.
Right, and just for the viewers, what Scott's talking about there is the neutral zone. I call it the gravitational neutral zone between the Earth and the moon. So as the Apollo spacecraft would have been on its trajectory from Earth to the moon, it would be constantly slowing down because of Earth's gravity. When it reaches the neutral point, where the gravity between the Earth and the moon is equal, then it stabilizes briefly, and then the moon's gravity takes over and increases its speed. So that's just so as everybody's clear on that.
So when you're reading it and you realize that they had to make a couple of course corrections to get to the moon.
Yeah.
They had to do a burn to get course corrections so that they get to the moon and hit the right spot going in there and meet up with the moon. And that's all highly technical.
Yeah.
Then you come back and you start reading on the third stage. The third stage makes it to the moon and crashes into the moon, and yet it's not up to speed to get there in the first place. It doesn't have any fuel, it doesn't have anything, it's not being remotely operated by NASA, it's just a blank tank of nothing, right? It doesn't have any controls, it's not anything, it's just the third stage. Just a dead shell. It's not up to speed. How does it get to the moon?
That's a very interesting point, because when they do the translunar insertion from the Earth to the moon, they fire, as you said, they fired the third stage rocket one more time. And that's supposed to put it on a trajectory. And that is supposed to have put them into an elliptical orbit. I'm just going by the official version here. An elliptical orbit that would set them on a path around the dark side of the moon and bring them back if the command service module engine had failed. That was with Apollo 11. I think Apollo 12 and on, they've changed that a little bit, but let's just go with Apollo 11. So that's very interesting. The question is, if they were on a trajectory to the moon, was the spacecraft slowed down when it had separated from the third stage to turn around and pick up the LEM? And then did the service module fire its engine to put it on a faster trajectory? Your question is how did the third stage itself get to the lunar surface? Is that right?
It wasn't going fast enough.
Yeah.
They had to fire the CSM, the service module, to accelerate another 2,000 miles an hour so that they had escape velocity. Then they had to make two course corrections so they lined up with the moon. Right. Yet this other piece of now space junk made it to the moon and crashed into the moon. That's where they recorded it ringing like a bell or whatever, right?
In your opinion, what should have happened to the third stage?
Well, it wouldn't have been able to escape if it did not reach escape velocity of the gravitational pull of the Earth.
Yeah.
It would eventually come back down and crash into the Earth.
Okay.
Right? Because if it's going straight out and it slows down, then it's going to come straight back down. It's like throwing a baseball up, it's coming back down again.
Yeah, no, I understand. I understand what you're saying. My understanding is that the firing of the third stage put it into a higher orbit, literally. It wasn't escape velocity from Earth. It would be a higher orbit, like an elliptical orbit, to include the orbit around the moon and back.
No, it didn't have the fuel to do that.
And it certainly didn't have that capability if it crashed into the lunar surface.
Don't forget, it already burnt once to get into parking orbit.
Right.
So now it's going around the Earth. That rotation around the Earth was supposed to be elliptical. Then they do the burn where they turn it and pull it away from the Earth to head to the moon. And it doesn't have enough speed to get there. It runs out of fuel.
Yep.
So then they pull out the command module, turn around, grab a hold of the LEM, turn it back around, give it another burn to accelerate another 2,000 miles an hour. So how does the third stage get to the moon if that thing needed to have another burn to gain 2,000 miles an hour farther? Right?
Yeah.
It doesn't have it. And yet it's recorded that it got to the moon. And yet the only way people could get to the moon, they needed to do that burn and have 2 course corrections.
Yeah, my understanding is they did, I believe, 2 course corrections, officially speaking, that is, in Apollo 11 there, and I think they did 1 on the way back, supposedly. When I'm talking about that for people, I'm talking, I go back and forth in context of the official version, and then, and then they add to it later.
Those little retros are going to change anything.
Yeah.
Like, they just go, point it that way. Well, you're still going that way because you're in space.
I have to look more into that. I have to look more into what you're saying, because
if you're not up to speed to escape the Earth's gravitational pull, eventually it's going to pull you back down again.
True, but the command service module didn't quite reach 25,000 miles an hour. It was below that, and that's why it was slowing down until it hit the gravitational neutral point, and then it sped up.
The documents I read said that the command module, when it did its burn, it went up to 27,000 miles an hour to get to the moon. And the third stage is left behind because it didn't have the speed to get up to that. And that's what I'm talking about. How does the third stage get there if they needed to do that burn to get that acceleration?
So you're saying it basically left the third stage behind. How did it catch up?
Yeah, how does the third stage catch up to that and get to the moon?
Yeah.
Right? It doesn't make any sense. Okay, and then they had to make a couple of course corrections to make sure that they got there.
Right.
And yet, this other piece of just space junk that's just floating around, didn't have the speed, managed to get there and crash into the moon.
Where in the documentation did you read where it says the command service module reached approximately 27,000 miles per hour?
And you can get it right on Wikipedia. You can read it right from there, and then you can go to the other documents off of that to read.
Off of that, and that takes you right to NASA?
Yeah.
Okay.
Yeah.